stories of that before, but I have not had that.
But there are some weird rules with the meet. So like, I know you as a teacher have to be the last one out of the meeting and stuff.
Oh, I didn't know that.
Oh, really? Oh, wow. Mr. Ryder makes a big deal out of it every time we do like his
So
I thought it was a rule. Maybe it's not. Maybe it's an easy
I think it's something you would want to have happen. It probably is a rule. I'm just probably an awful person.
I saw something where somebody like waited for an entire 24 hours in like their history class meet. So they were the administrator when the teacher and the class joined the next day. And
really?
Yeah. Well, the way I think I have it set up, it's a different code each time. So I think you can't join unless I'm there, but I'm not sure.
We can.
Okay.
I've tried to join like before you get there a couple times, like 5 minutes early, and it's like, you know, you have to go somewhere else to generate a new link. This one's like reserved or something.
Yeah, I think if the way I did it was, if I had it scheduled like in the calendar, I think you could get in. But I don't know. Anyhow, how to use a differential equation in physics. So by definition, a differential equation is a calculus function where the answer to an equation depends on the same variable, or how that same variable is behaving in the equation. That's a lot of words. So basically the idea is the rate at which a variable is changing will affect on the value of a variable at that instant in time. Jack, is that you? I don't think so. Okay, moving along. Yeah, it was worth a shot. At any rate, usually the way we think about this is we think about friction or drag. And oftentimes friction on a surface is constant, no matter what the speed. But sometimes the AP will say that it changes. And in reality, there are certain conditions where it does change. So when we think about friction being a constant amount of force with solid surfaces, like wood block on a table, like you might have done in a lab last year, that's true. But for things like tires, it's actually complicated. Because when tires get moving faster, they get hotter. When they get hotter, they get softer, and they get gummier, and they get more friction that way. So that's why, like when Julie is like revving up her car when she goes to the National Trail racetrack, right? Yeah, you get there and you brake, you torque it, and so that way you spin the wheels and they go on really hot before you actually launch. So it's kind of fun to do that. So I'm going to give an example up here. So we're going to say, assume a ball of mass M. I'll get this stuff down to see how much I'm going to write pretty big. Yeah, that's good. Mass M is released from rest at the top of a building. It experiences a force of air resistance. Experiences is a tough word. Air resistance, where that force is equal to negative kV squared, where K is a positive constant. Assume positive direction is downward. At the end of this, I will turn the camera around to each of you if you feel comfortable and leave Jack a message. That'll be fine. Okay. So normally with this, we would say express all answers in terms of variables. So express all answers in terms of M, K, V, and fundamental constants. So the first question I would ask you about this is, does the magnitude of the ball's acceleration increase, decrease, or remain the same after it's released? So I want you to think about that for a minute. I'm going to write it up here. Now talk to at least one other person other than me.
All right, Jeff,
Sorry to read, I'll try to that.
okay.
Drag is gonna eventually determine the velocity. No acceleration. It's gonna decrease. When that happens.
I agree. I say decrease, because if you think about it, at the moment of release, when there's not much drag built up onto it, as it goes down, it gets more drag force.
You know what, I agree with that now.
What did you come up with?
Decrease.
What did you come up with?
Decrease.
Okay, and can you explain why it was decreased, Theo?
Because when it's first dropped, has not very much drag acting on it, and as it progresses to the fall, more drag acts on it, increases the acceleration.
That-
Force going up.
That makes sense. Now, sometimes the way it's written is they'll say F equals kV squared. Even if there's not a negative here, if it's a friction force or a resistive force, you know that you're going to subtract it off of something else. So they're not always consistent in the AP with how they tell you this, but you should always recognize it's going to oppose a change in motion. So I would agree with that, but that's going to be a decrease. The next part of this, which would be a bit tougher, would be right, but do not solve just looking to see how much room I have. Differential equation for the instantaneous, that's a big word, velocity v of the ball in terms of time t. As it falls. Almost every time you think of writing a differential equation, you should go back to thinking of Newton's second law. A equals net force over total mass, or F net equals mass times acceleration. If we were taking the electricity and magnetism test also, there's one other case where we would see it. That deals with something called electromagnetic induction. But whether it's air resistance or drag on a surface or some other thing, I've almost always seen it relating to Newton's second law. And actually, I think even in that electricity example, it relates back to Newton's second law. So I'm going to start with that. So I'm going to say F net equals M times A. So that's where we start. F net is equal to what? In this case, what are the actual forces acting on that ball as it's dropping?
The force of gravity and the force of drag.
How would I write that? I would agree with you. How would I write that mathematically?
F grav minus, I guess just
minus drag.
drag F, because it's F over there, so,
Wait, it's F where?
like in the problem, so the force.
Oh, yeah.
Just use
Okay.
F.
Yeah, it would be F or something like that. I'm not there yet, but I would be. So I'm going to do this just real quick. So that's an intermediate step. That's definitely not, I would never leave it in those particular terms. So something like that. What's another way we can think of acceleration?
Change in velocity.
Uh,
The rate at which it changes.
okay, we're getting there. How would you write that in calculus land?
V prime.
A, acceleration is the rate of change of what with respect to what?
Velocity with respect
Right,
to time.
so
It is velocity with respect to time. So we're going to think about this as that. That is what turns a regular force equation into a differential equation. That's it. So in fact, when I think about this now, if I say F grav mg minus kv squared, because that's the drag force, equals m dv dt. That is basically your differential equation. And if it says write but don't solve it, that's all you need. You could rearrange it to put dv dt all by itself, dividing both of these by m, but you don't have to do that. So right there, on an AP free response, they'll probably tell you to do that at one point. And if you stop there, you're getting the credits for that. At some point, they may ask you to actually solve the differential equation. And in that case, you need to take an integral, maybe separate variables, things like that. We're not going to do that right now because we don't need to do it right now. And oftentimes on the AP exam, if they ask you that step, it is not worth your time to try to do it. If it's a simple equation, it could be. But sometimes they'll have an exponential decay or something like that. And just the math of doing, yeah, you're shaking your head. The math of doing that out of a 15-point problem might be 3 points. And maybe you might get one by putting 5 minutes into it. And yet you only have 15 minutes really to do the whole problem. So definitely, it is rarely worth your time unless you are ridiculously quick and good with math. I'm not saying don't look at it. I'm just saying most of the time that's what I've seen. But doing this is very doable, I think. All right, so then the other part here, and I'm going to have to go back over here. So I'm going to probably erase something else. So we've got this done. The next part would be to determine the terminal velocity of the ball. Julie, what's something you know that happens at terminal velocity?
Acceleration is 0.
Exactly. So I can go back to use this equation and think that m times 0 is 0. So I can use that and I can say mg minus k, this would be vt for v terminal, squared is equal to 0 at terminal velocity. So now I can say mg is equal to k vt squared. mg over k vt squared, square rootage the whole thing. I think that's the appropriate term. I definitely think that's something you can do, right? And then the last part of the example that I'm giving you today would be to make a graph related to this. So I'm going to show you axes. I'm going to ask the sketch a velocity versus time graph from the ball's flight until it reaches terminal velocity at time EF. Hey, Chad, say something nice about Jack.
He's smart.
He's smart. Hey, Garrett, say something mean about Jack. You don't have to do that. That'd be so rude. Yeah, I got all your consent. We can say whatever we want. No. The axes below. Sketch. Velocity versus time. And they'll normally say something like label axes quantities and asymptotes clearly. I don't know if that's the exact wording, but it'd be something like that. So what they would give you would be something like this. I'll put it in red. So I want you to think about the general shape and how we would label the axes, meaning what goes on this axis and what goes on this axis. The units don't really matter at this point. I mean, this would be in seconds, that's meters per second. What do you think the general shape would be of this thing? I saw two swoopies like this. So concave down.
Yes.
So leveling off something like this, because it said all downward motion was positive, so it definitely should be going up. They might try to fool you by having this below zero also. Okay. And on this axis, I should put this as TF. I should show that I've got an asymptote here. And on this axis, I should put radical mg over k. And that's it. Okay? Overall, okay? Now, I noticed Chad was being a good person by writing this down. Did you feel it was better to watch than to write down?
Yeah, for me.
That's okay. The fact that we are going to have a video of this might be useful at some point to write something like this down. But like I noticed earlier, it's like writing and talking and so forth is kind of difficult.
Yeah.
So almost always take this form, except like I said, a lot of them on the AP will say later on in the problem, now solve the differential equation. We are going to work with that right now. But so. All right. Well, you already said something. Anything you want to say to Jack while he's gone?
Good job.
I hope
Physics. That's all I gotta say.
That's exciting.
Stay safe.
Yeah, nice. Look at her just finishing up with making all of us look like crap. Wow. I kind of agree. So, physics. Oh, and we do have your I Heart Physics lanyard. I put in your mailbox, by the way.
Yeah, I still have